Hello, I'm starting a new series on clocking circuits, and in the clocking circuits, the most important system which we deal with is a phase lock loop, and I will, share with you why a phase lock loop, right? So basically, the background covered here in this series is going to be phase lock loop, also known as PLL. Now, question is, in any communication system, what is the use of this PLL? So in any communication system, you need a carrier, right? So it is used to generate a carrier frequency, right? So it is used to generate a carrier frequency. Now, what is the function of a carrier frequency in any communication system? So we basically have classic analog modulation. Now in analog modulation, we have got amplitude modulation, phase modulation, and frequency modulation, right? So these are different forms of modulation in analog. Now these days we are working with digital modulation schemes. Now the most common one which we are working with is known as QAM. In QAM we modulate, it's a form of phase modulation as well as amplitude modulation. And we if I consider a rectangular coordinate system, then a carrier is a phasor, right? And let's say we are talking about QAM 16, for example, then we have got 16 bins. So these are also known as symbols. And what we are doing is we are transmitting uh, a particular amplitude and phase. So for example, so let's say if this is 16 states, then you can combine 4 bits, right? B3, B2, B1, B0. 4 bits you can combine to form one symbol, and that is used in QAM 16. So that means that there are 16 states which can be coded, right? Now each bin represents a phasor amplitude, right? So there is a phasor amplitude, and then there is a phase, right? So for each bin there is a unique amplitude and phase, right? So that's what we are transmitting, right? And as the number of bins increase, right, the data which can be transmitted keeps on increasing, right? So the idea is, if I can code more bits as a particular phase and amplitude information, right, of the carrier, then more the number of bins, more data I can transmit. And second thing is, this would require, now if this is a polar representation, so there is an amplitude and there is a phase, but this can also be represented as I and Q signal, right? So that means that we have two quadrature signals, so there can be a rectangular component to this, right? So there can be I component and a Q component, right? So whichever you want to take, I and Q, doesn't really matter, right? So a rectangular a polar representation of a single symbol can be converted to two signals which are basically orthogonal to each other, I and Q, and I can represent them as the two axes, right? So these two axes are orthogonal, one represents I, other represents Q. So this is a rectangular coordinate system. So I'm transmitting two signals for a given signal, for a given symbol or a set of symbols. I'm transmitting two signals, I and Q, right? And if I change anything with I and Q relative to each other, then this constellation is no longer going to be as you see it. It's, for example, if I was to introduce a amplitude imbalance, then this entire thing is going to rotate, right? So that's going to happen, or it's going to skew, or if it is non-linear, then these symbols may move inwards, right? So all these things are there. So this is a form of you can say quadrature amplitude modulation, and this is most commonly used in communication system these days. And what is required for this is a carrier frequency. So this is PLL basically generates a carrier frequency that is modulated by the signal and transmitted, and when it's received it is demodulated and you get the signal back. Now what is the role of the carrier, right? Carrier is supposed to be a pure tone. So let's say if this is a carrier frequency, I do not want anything besides this carrier frequency. But in reality what happens is there is a noise in most of the electronic circuits which is up converted to the carrier frequency, and it exists around this carrier frequency. So what does this do? This introduces additional components adjacent to your frequency of interest, and the idea is if I can minimize this, then I would have a better a better performance. And when I talk of performance, better bit error rate or something like that. Now what are these additional components going to do? Now if you know that if you have a single frequency, then you would receive any signal as is. But then if there are other frequency components, they are also modulated, right? First thing is you are putting power into other spectrums, which is waste. Second thing is that this will interfere with your demodulation, right? So the idea is the purer the tone, the better it is going to be, and this is done by a phase lock loop, right? So what is the idea behind a phase lock loop? The idea is I have a oscillator which is a free running oscillator, and it has a certain control voltage and it has an output as a frequency. So then this is a block which has a gain of kVCO, which is basically delta F by delta Vc, right? So what are we doing? We are giving a control voltage and generating a frequency. Now the issue with this is the following, that let's assume a sine wave, right? And we are supposed to produce this pure sine wave, and then there are these zero crossings, right? Now because of the noise, these zero crossings can slightly shift, right? So they can slightly shift like this, and this can be this can be a random process, right? So they can take any value which is nearby this zero crossing, right? So this is a form of a phase noise, right? And the idea is to stabilize this VCO so that we can minimize this phase noise. And this phase noise is nothing but this is a noise which is up converted from the devices, right? And then there is a Leeson model which I have discussed in another series, so I'm not going to discuss that over here. Maybe later on I would cover that. So what do? We want to stabilize the VCO with respect to a reference, and that reference is a crystal, and crystal is going to give you a very good phase noise. Now when we talk of phase noise, we talk of single sideband phase noise, and what that means is I'm looking at a carrier which is FC, and then we are plotting on the x-axis offset, right? And then we are looking at the magnitude of the carrier, right? So this is the carrier which is of our interest, right? So let's say that this is the carrier of our interest, but then around this we have something which is not of our interest. So basically it decays, and it decays something like this. So we are talking about certain offset. So let's say this is going to be 10 kilohertz, and then let's say 100 kilohertz. So this is a log scale, 100 kilohertz, and then we are talking about 1 megahertz, 10 megahertz, 100 megahertz, and so on. And then we are looking at what is the carrier, what is the value, corresponding value of that spectrum relative to the carrier. So that is usually measured in dBc, okay, per hertz. So this power is measured over a single hertz. So basically that's the unit of phase noise, and this is specified at certain offset, right? So this is at certain offset frequency. So this offset frequency is to be specified. Now typically these crystals are very stable, and they can be two kinds of this crystal. One is TCXO, other one is OCXO. Now TCXO is a temperature compensated crystal, right? So it's basically phase noise is stable over temperature, right? And OCXO is oven compensated crystal oscillator, right? Now this one is basically you are responsible for providing a feedback which is based on sensing the temperature. So there is OCXO which can be more stable than a TCXO, but for most of our practical application, TCXO is good enough. So this provides a reference frequency here. Let's call this as FREF, right? So I get FREF out of this. Now what do? I take this frequency, which I say is FO, and I divide it by a certain factor, right? And that factor, let's say, is N, right? And then what I do is, when I come here, I have a block which is known as PFD, or it is known as phase frequency detector. So this is so the first block is going to be, so I'm going to list all the blocks. The first block I've seen is a VCO, which is a voltage dependent oscillator, right? So it's a voltage controlled oscillator. It has a certain gain, right, KVCO, which is del F by del VC. So that's a VCO. Second thing which we are seeing is a divider. This is also known as a prescaler, right? So that's a prescaler. The third thing which we see is a phase frequency detector, or a phase frequency detector, okay, or PFD. So what does it do? What it does is, let's say that this is our reference signal, right? So this is our reference signal, and then we are going to receive some signal which is basically delayed. So it is delayed in phase. So what it's going to do is, corresponding to this delay, it is going to generate a pulse, right? And similarly over here, this is delayed, so it can operate only on the one edge, or it can operate on both the edges, right? So let's say it operates on only one edge, right? So let's say this is a up pulse. So what is the up pulse telling it? Up pulse is telling it that the phase is coming as delayed. Why don't you up the frequency so that this phase catches up with this phase, right? And then this pulse disappears. Okay, so that's the idea. Now if you can also imagine that if this was coming earlier here, for example, right, it's coming earlier here, then it would have generated something called a down pulse like this, a down pulse like this, right? So PFD is generating up pulses and down pulses, right? And this basically is controlling what is known as a charge pump. Now this is a classic analog phase shifter, and there can be a replacement of these analog blocks by digital blocks, and which we will cover in what is known as all digital phase lock loop, right? So that will come later. First of all, we would try to create a phase lock loop here. Now after this, the output of PFD, which is up and down pulses, up and down, they are given to a charge pump, and this is usually what you call as a zero dead zone charge pump. And what is zero dead zone? So what is zero dead zone is, what happens is, this is some kind of a state machine, right? And then there is a basically there is a form of a feedback in here which has a certain delay, right? This causes a certain region of this phase of this charge pump to be not responding to the input. So basically in that region the charge pump doesn't respond. Okay, so what do I mean by that? I mean the following. So let's say I am taking the output voltage of output voltage of a charge pump, and then these up pulses are coming or down pulses are coming. So what is going to happen is, let's say we start from here, and if I receive these up pulses, then the charge on this is going to integrate and then saturate at some point. Similarly, if I have down pulses, then this is going to integrate and then it's going to go down and then saturate somewhere, right? So we have got up pulse taking the voltage up and down pulse taking the voltage down, and this voltage is a control voltage which is controlling this charge pump, this VCO, right? So that's the whole idea. Now the issue here is, this one is a high frequency, this one is a high frequency, and when you integrate, what you want to do is you have to put in here a low pass filter. So following this, you have something called a loop filter or a low pass filter here, and the output of a loop filter is given to the control voltage, and this basically completes your phase lock loop. So you understand what's happening. What's happening is, we want to lock the output frequency in phase with the input frequency, and the way to do it is we divide this frequency by a number n, so that at this point it matches, okay, FREF. So the idea is to match this to FREF, and that means that this VCO is not free running now. This VCO is locked in phase to this crystal, and crystal has very good phase noise characteristics. So what's going to happen is, if I was to draw in the same diagram, I can show you what is happening, right? So let me just show you what happens to the phase noise. Okay, so what is going to happen is, a free running VCO would have a higher phase noise and then it rolls off like this. But as soon as you put a loop filter, then in this loop bandwidth, okay, this is going to follow, going to follow the crystal. So this is going to follow the crystal, and then after that it catches with the VCO, right? So in this region, okay, which is the loop bandwidth, the phase noise of this source is the same as the phase noise of the reference signal. So that's the idea here. And what is the frequency generated? Well, the frequency generated is, so we have F naught and we divide it by n, and then that should become FREF, right? So F naught is going to be n times of FREF, right? So this is how this works. So the final block here was a loop filter, right? So the output of a loop filter is a control voltage, and that control voltage drives the VCO, and then the VCO output frequency is controlled such that F naught is equal to n times of FREF, right? Now this has a few, problem areas, and I will talk to you some problem areas. So for example, this filter was 40 megahertz, right? And this is an integer. So if this is an integer, that means F naught is going to be n times of FREF. So basically that means that if you want to shift a frequency by changing n, right? So if I change n as an integer, then the output frequency will go in the multiples of 40 megahertz, right? So there is a problem here which you can see. Let's say over a period of time with aging, this crystal, okay, shifts in frequency from 40 to, let's say, 40.02 megahertz. If that happens, then depending on the n, so the change would be n times of 40.02, and there is an error of n times of 0 times 0.02. So this is going to be an, I can say this is a error. So error would be introduced because of aging. So aging can cause this error to happen. So we want a PLL where this can be corrected at this point itself, rather than changing the PLL. Another thing which can happen is, over temperature, this frequency can also change. So one problem here is the aging. The other problem here is that temperature dependence of this crystal, right? So again, it is a temperature compensated crystal is going to be much better, or a oven compensated you know, crystal, that is going to be, you know, much better compared to a normal crystal which you see. Now these are the two variations in the reference frequency. The third thing which is problematic is that, for example, we have a band. Okay, let's say that band is going to be from 2.4 gigahertz or 2400 megahertz to 2500 megahertz. Okay, now the problem is, if I was to use this fixed N, then I would be going in steps of 40 megahertz. So the things which I could do would be 2400, 2440, 2480, and then I would not even have, you know, 2500. Actually I will go to 2520. So you can see that this crystal fixes the steps. So I could only generate 4 carriers here in this band: 2400, 2440, 2480, 2520, right? Now I might need more carriers than this, right? So one solution to this would be you lower the frequency of the crystal. So let's say I went to something like 5 megahertz. Now I can do 5 megahertz steps here. Okay, so I can go 2400, 2405, okay, 2410, and so on, 2415, 2420, and so on. I can go up to 2500. Okay, so now what has happened is my reference is now 5 megahertz. Now let's see what's happening if I go from 40 megahertz to 5 megahertz, right? And I will explain you why that is problematic. Okay, that is problematic is this way. Now consider that this is an observer. Okay, PFD is observing two signals. It's an observer, and then it is comparing and then producing a certain output, up or down pulses, right? So it's an observer. Now F naught is my output. So F naught is divided by N, and then I'm observing at the step which is going to be basically so for example, let's say we have a certain time period T for this one, then over here the time period will be NT, right? So because I'm dividing the frequency by N, so I'm multiplying the time period by N, right? So over NT time period, so I'm comparing on these edges, right? So these edges are differing by a time period of NT. Okay, so when this happens, what's going to happen? More or I'm doing a mistake, 1 over NT, sorry. Okay, time period is multiplied by N, right? Because it's dividing the frequency by N. So yeah, correct, it is NT only. Okay, so for example, let's say I am using a 5 megahertz crystal versus 40 megahertz crystal. Then I'm trying to generate 24 megahertz, for example. Then 24 by 5 is going to be my N, right? So this is going to be 5 4s are 20, and then it's going to be 5 8s are 40, 480. So N is going to be 480, right, in 5 megahertz. In 40 megahertz crystal case, the same thing is going to be 2400 divided by 40, which is going to be 46, so 60. So in this case N is 60, right? So if it is 5 megahertz, N is 480, and if it is 40 megahertz, N is 60. So that means that it will be, in this case, what is going to happen is, for the same frequency, in one case I have got 480 times of time period, right, which is basically 1 over 2400, right? So let's say T only. In another case it is going to be 60T, So this case is when it is 5 megahertz reference, and this case is when there is a 40 megahertz reference. Now the issue here is that this time period is 480t, sorry, in case of 5 megahertz, and this time period is 60t in case of 40 megahertz. Now let's assume that this observer is seeing the situation on these edges, which are separated by 480t or 60t. Now let's assume like this, that this PLL is locked, let's say, to the reference, but now it is gradually falling off. Okay, so if this is gradually falling off, so it is locked to these edges, but then it is gradually falling off. So if I spend 480t, it will fall off more, so that error will accumulate more over 480t, and the same error over 60t would be much smaller, right? So because you have a reference which comes earlier, right, you make a correction earlier, you don't allow it to drop much more before comparing, right? So basically, if the time period between the two comparisons, right, by this PFT is separated by 480t, then the frequency can deviate more as compared to 60t when it's going to deviate less. So you understood the problem here. The problem is, if I have a large divide ratio, there are two things which can happen. One is it will be allowed to fall off, and then it will catch up again. So basically it will unlock and lock again. So this is going to give you some kind of a jitter or some kind of a response, which is basically FC. And then there are frequency components here which are called spurs. Now these spurs, okay, if they are continuous in nature, like there are lots of them and it becomes a spectrum, then it is called a phase noise. Otherwise, if these are distinct frequency components, then they are called jitter, right? So there is a basic difference between jitter and spurs, jitter and phase noise. Phase noise is a continuous spectra, while jitter is distinct frequencies. So now if this divide ratio is large, then we are going to have certain jitter around this. Now if this is a continuous spectrum, right, 480t, the variation or the error is basically not just fixed error, but it is continuously varying over a certain range, then you are going to get a phase noise, right? So you understand, as you increase the divide ratio, the phase noise is going to become worse and worse, right? So larger the divide ratio, okay, worse is the phase noise. And second thing is, this is a DT approximation of a CT system. So what do I mean by that? It is a discrete time approximation of a continuous time system. Now if I was to do this analysis of this loop in continuous time, this doesn't guarantee the stability of the loop, right? In a discrete time, the divide ratio is telling you that I have a sampling frequency which is separated by 60t or 80t, where I am comparing the DT system with a CT system, right? So in a CT system, you are continuously comparing. So basically it's not that you are comparing at this edge and then you are comparing at this edge. You are continuously comparing. So CT system you can design for stability, but then DT system also depends on what is the sampling rate, right? If in one case the sampling rate is 480t, other case the sampling time, okay, or the sampling step is 60t, right? So if you do 60t, you are comparing more often compared to 480t. So this loop will not fall off or will not become unstable, right? So this can also be shown in terms of Z transform, and in that case there is a relationship between the sampling frequency and the output frequency, right? So the sampling frequency and output frequency ratio, right, is, if it goes beyond a certain permissible limit, then the response goes out of the unit Z equal to 1 circle or a stability circle. and then what happens is it is unstable. So digital systems are going to be unstable if the sampling rate is not correct for a given output frequency. So I hope you understand. Now to sum this up, let's say that there is a line following robot. So this is a robot, and this robot is checking okay, at different steps over a period of time. You can say different steps in time, or this can also be said different steps in length. So at this point it is making a comparison, at this point, at this point, at this point, and at this point. So the robot is basically following this line and it is deviating, and at this point it says that the line is on the right hand side, so let me make a correction. So it made a correction, right? And then it said, oh, I have overcorrected, now let me make a correction again, right? So it's going to go this way, and then it is going to make a correction again, and it goes like that, right? So now if these points where the correction was made is kind of doubled, like, you know, at this point, then the same robot going with the same rate, for example, is corrected here, then it will be going this way, and it will be corrected over here, and then it will be corrected over here, right? So this error which you have accumulated is now more compared to the error which accumulated when you more frequently, you know, compare. So I hope you understood what do you mean by DT approximation of a CT system. In this case, okay, if for example, if your sampling frequency is not high enough, what may happen is this robot will no longer be able to do a correction, or rather these values are going to keep increasing, and the robot is no longer following this line. It basically just, you know, after some point it just deviates to a point where it cannot come back, right? So this is an example where I wanted to show you that if there is a DT approximation of a CT system, then there is a certain sampling rate, right, for a given frequency, for which you have to, you know, make the correction so that it remains in a certain, you know, certain tolerance. Otherwise it's going to become unstable. So you understand that n basically cannot be very large. If n is very large, there is a problem. The problem is, first of all, this phase noise is going to go up because you are making less frequent comparisons, okay? So as the n goes up, the phase noise is going to go up. It is not going to lock to closely to a crystal, right? So that's what's going to happen. And secondly, then the loop may itself become unstable, right? So that these are the things. Now CW system is stable, then this is the this is basically the loop filter is deciding the stability of this loop. But in a DT case, is the sampling frequency or the loop bandwidth is important, or this n is also important here, right? So if you keep increasing n, you are accumulating more errors and it may become unstable. So that's why we don't keep large n. Now this causes more problems. Why? The problem is the following. If I am allotted a certain band, okay, and that band goes from 2400 megahertz to 2500 megahertz, right? Now the issue with this is, if my carriers or subcarriers in here are separated by 1 megahertz, then I am supposed to use a crystal which is going to be 1 megahertz because this is a fixed n, right? So can I have 40 megahertz crystal and still generate, okay, so still generate the output frequency which in steps of 1 megahertz, right? So that's the idea, okay, without compromising on the divide ratio, right? So for example, if I have 24 megahertz and I want to generate 2402 megahertz, correct? So what would be the divide? Let's say my crystal is 40 megahertz, and here the crystal is same 40 megahertz. Now here I would just say that the divide ratio is going to be 60, correct? So the divide ratio here is 60, while here the divide ratio is going to be, so if I divide 2402 by 40, so that will be 24.2 by this, so that is going to 46240, and then you have got 0.5. Am I right? So then the divide ratio here is going to be 60.05. Now the question I would ask is, can I generate a fraction? Okay, so can I generate this n, which is no longer a integer but it is a fraction? So that's that's what is done by a fractional N PLL. Fractional N PLL. Now how do you do that? Okay, it's very simple. Let's say I divide, okay, so this is a small number. Let's say I divide by 61 sometimes. So let's say I divide this by m number of times. I'm going to divide by 61, and n number of times I'm going to divide by 60. So basically I am dividing by 61 m times and 60 n times. So can I have an average which is equal to this? So basically system is responding to the average of the two numbers now. So one is happening m times, other is happening n times, and over a period of m plus n times I am achieving a fraction of 60.05, and this is what is being done in fractional N PLL. What we are doing is, instead of dividing by a fixed n, we are dividing by n plus 1. Okay, so if I am dividing for certain number of cycles with n and then n plus 1, so basically let me represent this as, okay, division by n and n plus 1. So n times I'm going to, small n times I'm going to divide by n, and small m times I'm going to divide by n plus 1, right? So when I do that, I can establish a fraction of n. And why would this work? It would work because this loop is a low pass system. So we are fooling the system here in a sense that this VCO basically is responding to a low pass signal. Because of the loop filter, it is responding to a slower signal. VCO is responding to a slower signal on VC. If the signal on VC is large, then VCO is not responding. So because it is a low pass system, right? And because of that, the n, fractional n, generates a VC which is going to be continuously, varying between two values. Like you can generate a fraction of VC. So for example, if this n generated VC1 and n plus 1 generated VC2, right? And if we were to basically do a multiple number of times such that the average of VC1 and VC2 is certain number between VC1 and VC2, that would appear here because this is a low pass system, right? So this is how a fractional N PLL works. And we will see if we have two fractions. For example, it is a dual modulus. So it's a dual modulus. Why? Because it is either dividing by n or it is dividing by n plus 1. So if it is dividing by n and n plus 1, then there would be, okay, so there is a fixed pattern. So let's say if I divide first with all n's and then all n plus 1, then there would be a carrier which is a fraction of, so it will be a fraction between n and n plus 1 times of, so I can say this is a fraction between n and n plus 1 times of, so this is a fraction, okay, times of fref. right? So this is my output, but there is a transition per cycle in the sense over n plus m cycles, m plus n cycles. Over these cycles, there is somewhere going to be a transition between n and n plus 1, and that is going to repeat over these cycles, right? Over m plus n cycles, this is going to repeat, and this will result in a spur. Now, if, for example, you randomize n and n plus 1, so you don't do like this. You divide by n and then you divide by n plus 1. Okay, so you divide by n for n small n times and then n plus 1 capital M times. Instead of that, you mix them or randomize them. Then this power which is in this spur is going to spread out, right, over a larger spectra, but its magnitude is going to go down, right? So you can randomize n and n plus 1. Now you can do one more thing. Why you are fixed to n plus 1? You can say I can go n minus 3, n minus 2, n minus 1, n plus 1, n plus 2, and n plus 3, right? So these are what? 1, 2, 3, 4, 5, 6, 7 states. I can take 8 states if I want. Okay, n plus 4. Okay, so I have, instead of using 2 states, I'm using now 8 states, and then they are pretty well mixed up, and that means that this would further go down like that. So what am I doing? I am taking the noise which is continuous like this, and basically I am taking it down. So initially it was like this, right? So I am basically making it, shaping the noise here. Okay, and this is being done by randomizing n and n plus 1, or rather randomizing 8 states now. 8 states. So if I randomize these 8 states over a fixed number of cycles, then I would be able to shape this phase noise. Okay, so that's the principle of phase noise shaping. Okay, and this is done by something called Sigma Delta Modulator. And what is a Sigma Delta Modulator? Its principle is also very simple. The principle goes like this. Let's say I have 50 students in a class. Okay, so I have 50 students in a class, and I take their heights, right? Their heights, and then I find a average height. Now, okay, maybe I should give you a different example, because let's say there's only one measurement which I'm going to do, not 50 students. Okay, let's say I have like a distance, for example. Let's say I have to measure a distance which is L. So I measure this distance L, let's say x number of times. X times I measure L. Right? So every time when I measure, there is a error with it, which is, let's say, delta L. Okay, so delta L1, then next time I measure is delta L2, next time I measure is delta L3, and this delta L can be a positive or a negative number. So how do I get this to be more accurate? If I measure it x times, then I sum all of them, right? And I average it out over x. So I have summed all the L measurements, and then I have divided it by x. So this is called averaging, right? So what did we do? We did a sigma here. You see, this is equivalent to an integration. And when we do an integration, these noises are going to cancel out each other. And then when we did a differentiation, that is divided by x, then we get back to the same value, which is our original value of L. And in this process, we have got rid of this noise. Now, this is a first order integration and differentiation. So I have got rid of first order noise. Okay. Now, if I was to do sigma 1, Then I was supposed to do sigma 2 and sigma 3. Like for example, instead of just correcting for delta L, we are correcting for or rather we are correcting for the second order, right? So how would I show that? So basically I am doing an integration. So instead of doing just first order integration, I do a second order integration, and then I do a third order integration, and then I do a differentiation second order, and then the first order, and then we are back. So what it means is we are averaging out not only on the first order noise, but we are also averaging of the second order noise and the third order noise. So depending on the order of the integrator, right? So this is what is happening inside a fractional N PLL, okay, and noise shaping. A sigma delta modulator basically is averaging out, and if I do first order integration and differentiation, that will filter out the first order noise. If I do a second order integration differentiation, then the second order noise will be cancelled out. If I do a third order, okay, and that is the final order, so basically I am compensating for first and second order, but for the third order I don't have a compensation beyond that. So that is going to be basically going to be higher frequency. So what is happening is that the noise is going to be shaped out like this, okay, and it again picks up on both the sides, and this basically is your loop bandwidth. Okay, and the order of integration differentiation, right? And then you are going to put a filter around it, and that filter, so in our case that filter is this low pass filter which you are putting here, right? So if the sigma delta is of third order, then you should have a filter which is of fourth order, or if the sigma delta is of second order, then the loop filter should be of third order. So the loop filter should be one order higher than the sigma delta, right? So we will see in more details what's happening here, and after this you can get spurs or whatnot, right? Okay, so what is happening is we are doing this noise shaping using sigma delta modulator, and we are pushing the noise from lower frequency or lower offset frequency to a higher offset frequency. So wherever, okay, up to wherever the corrections are done, okay, you get low phase noise, and beyond that it is uncorrected, right? And then you put a loop filter around it. Now these loop filters are also, some things which you have to see is, first order, second order, third order loop filters, and we will prove it, are basically stable. And beyond third order you are going to see complex poles, and complex poles means ringing, right, or spurs. So that means that for a stable system you can go up to third order loop filters, and we'll prove it. Why can't we go beyond it? And if you want to study this, there is a nice textbook by Dean Banerjee or Gardner, where you can see that what order of filter you can put there and which order filter is going to be stable. Okay, so enough about phase lock loop. Now let's see how much time have I spent here. I have spent 48 minutes in here. So here I am going to just reinforce your learning, okay, and I'm going to show you in a practical design. I'm going to show you in a practical design all these blocks. So let's list those blocks and see them one by one. So first of all, I am going to see a VCO. Second, I am going to see a multi-modulus frequency divider. It is multi-modulus frequency divider. Third thing I am going to see is a Sigma Delta Modulator. Okay, Sigma Delta Modulator, right? Fourth thing I'm going to see is a phase frequency detector, or PFD. Okay, fifth thing I'm going to see is a charge pump, and sixth thing I'm going to see is a loop filter, right? So these are the essential blocks of a analog PLL, right? And this is a fractional N PLL, right? So let's see these blocks in ADS. So over here I have a finished block, and this is a fractional N PLL for two bands. One is 2.3 to 2.7 gigahertz, other is 3.3 to 3.9 gigahertz. So this is for Wi-Fi WiMAX. This was done far, almost like 15 years back when WiMAX was picking up. So that technology is obsolete now. There was no WiMAX. Okay, and then besides that, you are seeing this loop filter, which is C1, R1, C2, and R2. And this loop filter is a third order loop filter, right? You can see what is establishing the order, right? RCs. So you can see that there is a combination of RCs. So basically there are two C's and R. So that will establish two poles. And then there is another R. Okay. So with that, there will be another RC time constant. So basically 3 RC time constants, and then there are going to be 3 poles. So this is a third order loop filter. Okay, so there is a final capacitor here also. So basically there is a 3 poles which are significant poles, and then this is a third order loop filter, right? And what you see here is the initial condition. In Cadence you can establish it in, when you are simulating it, but here you have to put these blocks for the initial condition. Okay, so this is a loop filter. So this is external to the chip. Now let's go inside this. Okay, let's start with a VCO. So this is a VCO, and this is a dual band VCO. One is a lower band, other is a higher band, and then there is a multiplexer, and that multiplexer decides whether I'm operating in lower band or a higher band. And if I go inside, I see an inductor here, and then 2 varactors here. So these are the these two form a tank circuit, and then it has a certain loss, and then there is these cross coupled transistors both at the top and the bottom, PMOS and NMOS. They provide negative resistance to compensate for the loss of the tank circuit, so that the oscillations should continue to take place, right? It should not just damp out. So this is a VCO, how it works. And then there is an output buffer. We may not have a buffer, but that's okay. And then this varactor are the 2 capacitors, right, which are controlled by this voltage we control. So there is a net voltage across these diodes, okay, which decides the capacitance, and that establishes the frequency of this VCO, output frequency. So by controlling this control voltage, I can control the output frequency. So same is there at the higher band side also, and then there is a multiplexer here, and then there is an output. So the output from a dual band goes to what is called a prescaler or a programmable divider. Okay, so in this case this is a 32 to 127 divider, and I'll show you how to do these dividers later on. Okay, so these are nothing but 2 by 3 cells which are cascaded, and in analog playlist you can see the design of this 5-bit or a 6-bit frequency divider. And then these are the interface circuits. Because this divider is operating at a high frequency, it has to be designed as a CML, right? So CML is like current mode logic. So the CML has to interface with CMOS. So these are nothing but voltage translators, you can say, or kind of a bridge, right? So you can design this. In case you do not have CMLs, then everything is going to be CMOS. And here it says this is an adder for Sigma Delta Modulator. So what it means is that the 3 bits means 8 states. So if you see here, there are, if I was to consider n minus 3 to n plus 4, these are your 8 states, right? So these 8 states basically establish n, okay, around n, right? So we have these 8 states are around, or 7 states are around n, right? So that those states basically are giving that 3-bit count, and that 3-bit count is added to the course count here. So that's what you do. You take course count, and then you add to it the sigma delta count, and then the average is going to be the fraction which you want to generate. the output of a sigma delta is going to be an average between 3 and 4. So if it is a 8 states, then I am getting an output which is an average between 3 and 4, and this is also covered in the playlist analog circuit design using ADS, right? So now let's go up. So there is a frequency divider, and the frequency divider, the 3 bits are coming from this Sigma Delta Modulator. So now if you want to see what is inside a Sigma Delta Modulator, there is a accumulator, right? So as I told you, m plus n cycles. So in this case it's going to be 2 raised to 16, because this is a 16 bit input, right? So it is going to be 2 raised to 16 cycles which are required for the average to be produced. And you know there is a trade-off. Okay, the trade-off is either you have a finer steps and better noise figure, okay, or you have faster settling, right? So then you are settling in lesser than 2 raised to 16 cycles, but in this case you require 2 raised to 16 cycles for the right average to show up, right? So you are doing a first order integration here, second order integration here, third order integration here, and in this network you are doing the what you call the differentiation, right? So you are doing the second order differentiation and then the first order differentiation, okay, and then you get back to 3 bits, right? So this Sigma Delta modulation is done using 3 integrators, 2 differentiators, right? So that's what is called mesh 111. So that's what I'm using here. So the 3 bits which are generated here are added to the coarse count, and that is given as input to the divider, and the output of the divider goes to a PFD, or phase frequency detector. And a phase frequency detector is basically some circuit. This is a zero dead zone phase frequency detector, right? And I have broken it into 2 halves, but you can do a one continuous circuit, and these are differential stages. So this everything is made up of what is called Ppcl gates, and this Ppcl gates I have covered in digital circuit design using ADS. So even these NOT gates are differential gates. You can see this is a differential Ppcl NOT gate. So PFD is fully differential here, right? And then the output of the PFD is the up and down pulses. So you have differential output, up up bar, down down bar, and this basically is controlling the currents. This is a current steering charge pump. So basically what it's doing is that either the output is charged by the source here, or it is discharged by the sink here. Okay, so this is a source circuit. The source is the current. This is a sink circuit which sinks the current, and the current is either steered into the load or steered to the ground. And for this one, the idea either the current is synced from the output capacitor, or current is synced from the top source. So basically it is a current steering charge pump here, and the output of current steering charge pump. And again, okay, there is one more stage here which is basically high impedance state. So what's happening is I don't want drooping to occur. So basically what happens is, because of leakages in this charge pump, there may be a drooping of the output voltage. So basically I can cut the output using, or by this gating, using a transmission cell. Okay, so this is a current steering charge pump, right? And the output of the charge pump is external. It goes to the filter out. Okay, so it basically goes to filter out over here, and then it goes back as a feedback, right? So this line you see is filter in, so that goes as a feedback. So let's go inside. So it goes out to a filter, it goes to a filter in. Now we actually don't use a op amp here. Okay, we use some kind of a follower, op amp has more delay in it, so you are introducing delay in the fractional N loop. So why this was there is because what happens is in these VCOs, right, when you go to a certain voltage level, these diodes, they start conducting. Okay, these diodes start conducting means that they are going to leak the charge. So if they are going to leak the charge, what's going to happen is, if this is directly interfaced to the output of a loop filter, okay, then loop filter wouldn't build a charge on its output capacitance. It would leak out, right? And to isolate that, you have to have a certain form of isolation, which is done by this op amp, but you can just use a simple differential stage here. Okay, so you don't have to be as elaborate as a op amp, so that will cut short the delay between input and output. So this is used as a buffer, but you can just use a simple differential pair. Okay, so that is given to a VCO, and the control voltage controls the VCO, and it gives you an output frequency. So basically you are going to get the output frequency, and what these are the outputs of the divider. Okay, so basically you are not only getting one frequency, but you will be getting just one second, QQ bar. So where is the output? Coarse input, fine input. Okay, so this basically is your quadrature. Okay, I'll tell you what is quadrature. So you remember that for communication system you are supposed to have I and Q, which are going to be modulated by sine and cosine or orthogonal waves, right? So for higher band you have got 0 and 90 degrees, and for lower band you have 0 and 90 degrees. So you can get, the either of the frequency band you can get the quadrature output. So that's that. Okay, and this over here you see C0 to C5. Okay, so that's your coarse input, and then there is a fractional N input. One more thing I wanted to show you is that in this case a sigma delta, a lower bit, okay, of course again establishes some kind of a spur in the output. So remember, for n plus 1 we were getting a spur, so we went from n plus 1 to we went from n minus 3 to n plus 4, 8 states. But again the LSB may be introducing a spur, and for lowering that spur there is something called a Dethering circuit. So there is this ring oscillator which is establishing a dethering on the LSB of a sigma delta. So that's what is happening in this case. So this is a fractional N PLL, and I have shown you all the blocks which I talked about: VCO, multi-modulus frequency divider, Sigma Delta Modulator, phase frequency detector, charge pump, and loop filter. And we will discuss this. So this is the block diagram which is showing, which I just showed you in the circuit. There are four outputs in 2 bands, and all the blocks are in here. And then I can show I have covered already a sigma delta in another playlist, but I'm going to redesign this sigma delta here. So what is this sigma delta is doing? It is generating an average between 3 and 4. Okay, so it is generating a count which is going to be n minus 3 to n plus 4, and such that the average is between 3 and 4, right? So these are the different steps over 2 raised to 16 cycles. So right now I haven't covered all the cycles, right? So the output will not stabilize to the final value, because n is still varying between coarse n plus 3 point something, between 3 and 4. That will be the fine n, which will be established by the Sigma Delta Modulator input. So multi-modulus frequency divider is nothing but a cascaded 2x3 cells. I have already covered this in the analog circuit design using ADS playlist, right? So this is that. This I have already shown you. This is a Sigma Delta Modulator. This is the Deterring circuit. This is the PFD, various states, right? And this is a zero dead zone, so that's what I'm trying to show you here. And this is the charge pump, and this is the high impedance current source and sink, and this is how the charge pump voltage builds up over, with the up pulses and the down pulses. So you see both sides, the voltage building up or building down, right? And that is controlling. This is the algorithm for computing the values, component values for loop filter. This I will cover in detail, how to place the poles, right? How to get a stable, a stable loop filter. And this is basically in ADS, it is programmed like equations, and you can give it various inputs to this, and we will talk about, various inputs like loop bandwidth, T3 by T1, or basically these are pole 3 and pole 1 ratio. Then there is a gamma optimization factor, phase margin you are targeting, and then K phi in KVCO. KVCO is the VCO gain, K phi is a phase frequency detector gain, right? And then there is a given divide ratio N. So basically I am computing from this all the filter component values, and then that filter basically is used, as I showed you here. That filter is used over here. So I'm computing these filter values, capacitor and resistor values from that algorithm, and this is very nicely given in Dean Banerjee, or I think in Dean Banerjee's book. Okay, so that would be that. So I am going to cover quite a lot of stuff here in this playlist for fractional N, multi-modulus fractional N PLL, right? And this is, I have already discussed in one of the playlist, what is the Leeson's model for a VCO phase noise, and what are the various sources of these phase noises, the short noise, the flicker noise, and all that. So that's basically, you can refer to the session in analog circuit design using ADS, right? So this is what I'm going to cover in this series. Various sub-circuits are in here, and we are going to design all the sub-circuits. We are going to lay them out in a process, and then we are going to integrate this to have an entire PLL, right? Fractional N multi-modulus PLL. Then later I'm going to show you a low power variant of the same PLL using all digital blocks, all digital PLL we are going to do. So this series is going to cover a lot of things on clocking, and if energy permits, I will also discuss clock recovery circuits in various systems, right? So I am going to stop here. Let's see how much time you're taking. Yes, I'm going to stop here, and just follow my videos, and you will be able to recreate this design, and you'll be able to learn this thing.